space itself is behaving in ways that defy our most trusted understanding of physics. When astronomers measure how quickly the universe expands, they don't get one consistent number, they get two, and the difference between them has shaken modern cosmology to its core. According to our best theoretical models, the universe should be stretching apart at roughly 67 kilometers per second for every 3.26 million light-years of distance. That's the prediction derived from fundamental physics, refined over decades of observation and calculation. But when we look at the cosmos directly, at galaxies near and far, at the flicker of dying stars and the pulse of ancient light, the result isn't 67, it's 73. That 6 kilometer per second gap may sound trivial, like the difference between two clocks that are just a few minutes apart, but on the scale of the universe, it represents two completely different realities. One describes a cosmos following the rules Einstein and generations of physicists built. The other suggests something unseen is forcing space to expand faster than it should. For years, scientists assumed the mismatch was simply a matter of error, tiny flaws in measurement, miscalibrated instruments, or perhaps the wrong assumptions built into the equations. But with every new observation, every technological leap, and every fresh check of the data, the gap refused to close. Instead, it grew more stubborn, more precise, and more undeniable. The universe is expanding too quickly, and nobody can explain why. This conflict between theory and observation has become one of the most dramatic scientific puzzles of our time. It's no longer just a statistical nuisance or a problem to be solved with better instruments. It's a fracture in our understanding of how reality works. When cosmologists point their telescopes at the universe, they are in effect measuring the heartbeat of space-time itself, and the rhythm isn't matching the beat predicted by our equations. On one side of the debate, researchers studying the faint afterglow of the Big Bang, the cosmic microwave background, trace the expansion history all the way back to when the universe was just 380,000 years old. Using that ancient light as a blueprint, they project forward through billions of years and arrive at a smooth, consistent model. An expansion rate of about 67. The math fits perfectly. The physics makes sense. Everything clicks. But when another group looks closer to home, measuring the speed at which galaxies are moving away from us in the nearby universe, they arrive at a completely different answer. They study supernovae massive stars that explode with predictable brightness. They measure pulsating stars called Cepheids, which brighten and dim like cosmic metronomes. Using these as cosmic yardsticks, they calculate distances with exquisite precision. Their result? 73. Two independent methods, both built on decades of scientific progress, both incredibly robust yet fundamentally at odds. Imagine standing in a room with two clocks. Both are brand new, both synchronized to the same standard, both running perfectly. Yet one insists it's 3 years while the other says 3:10. You check them again and again, but the discrepancy doesn't vanish. That's the situation cosmology finds itself in. These aren't guesses or speculative theories, these are hard measurements, confirmed by multiple teams using different instruments. Even the James Webb Space Telescope, with its cutting-edge precision, has weighed in, and instead of resolving the tension, it made it worse. Webb confirmed that the higher expansion rate measured locally is correct, reinforcing that the disagreement is real. The crisis isn't about a single wrong number, it's about what that number represents. If the universe expands faster than physics predicts, then something fundamental, something baked deep into our laws of nature, is incomplete or misunderstood. It's as though we've been reading reality's instruction manual, only to find that entire pages are missing. Over the last decade, scientists have exhausted every obvious explanation. They've checked for faulty detectors, recalculated uncertainties, questioned the behavior of stars used for measurement, and reconstructed models from the ground up. Every test comes back the same. The instruments are accurate, the methods are solid, the discrepancy is real. What's left is a mystery so deep that physicists have started to call it a crisis. They're not exaggerating. The expansion rate known as the Hubble constant is one of the foundational parameters of cosmology. It defines the age of the universe, shapes our models of how galaxies form, and influences how we understand dark energy and dark matter. Getting it wrong means rewriting the entire history of the cosmos. The numbers on the page have become a challenge to the laws of physics themselves. Some scientists now suspect that something beyond our current theories is at play, a hidden ingredient, a missing law, or perhaps even a new form of energy that acts across the fabric of space-time. Others go further, wondering if time itself might not flow uniformly everywhere, or if gravity behaves differently across cosmic scales. Whatever the explanation, the stakes couldn't be higher. This isn't just a story about numbers, it's a story about the limits of human understanding. When we look into the dark, ancient distance and see the universe expanding faster than it should, we're not just measuring speed, we're measuring the boundaries of knowledge itself. Something, somewhere, doesn't add up, and solving that contradiction could mean discovering a completely new chapter in the story of existence. To understand why scientists are so unsettled, we have to look at the two different ways humanity measures the expansion of the cosmos. Both methods are brilliant in their own right, elegant and time-tested, yet they rely on entirely different kinds of evidence, one peering into the distant past, the other surveying our cosmic neighbourhood in the present, and somehow each tells a different version of the universe's story. The first approach reaches back almost to the beginning of everything. Astronomers analyse the faint microwave radiation left over from the Big Bang, the afterglow that still fills all of space more than 13 billion years later. This ancient light, known as the cosmic microwave background, carries subtle fluctuations in temperature and density, tiny fingerprints of the universe's earlier structure. By studying these patterns, scientists can infer how much matter and energy existed back then, how gravity shaped that material, and how fast space was stretching in its infancy. Using the laws of physics, they project those conditions forward through time, calculating how rapidly the universe should be expanding today. The result, after decades of refinement, lands at around 67 kilometers per second per megaparsec. It's a triumph of theory, observation, and mathematics woven together into a coherent model, a snapshot of the universe's birth, expanded into a full cosmic biography. The second method doesn't look backward. It measures the universe as it is now. Astronomers build what they call a cosmic distance ladder, an interconnected system of measurements that begins with relatively nearby stars and extends outward to galaxies millions of light-years away. The first rung involves Cepheid variable stars that rhythmically brighten and dim in a precise pattern. The rate at which they pulse directly corresponds to their intrinsic brightness, allowing scientists to calculate their distances by comparing how bright they appear from Earth. Once the distances to these nearby Cepheids are known, they serve as calibration points for measuring much farther objects, especially Typeia supernovae, which explode with consistent luminosity. These supernovae can be seen across vast stretches of space, acting as cosmic lighthouses that mark how quickly galaxies are receding from us. The relationship between their apparent brightness and their red shift, the stretching of their light waves as space expands, reveals the present rate of cosmic expansion. And when that number is computed, it consistently emerges higher than predicted, roughly 73. The precision of these techniques is extraordinary. Teams working independently on different continents, using different telescopes and instruments, keep converging on the same answer. The local universe really does appear to be racing apart faster than it should. If the two measurements overlapped within their margins of error, the problem could be dismissed as statistical noise. But they don't. The gap between 67 and 73 is wide enough that chance alone can't explain it. It's not just a matter of rounding differences or experimental imperfections. It's as if two historians studied the same ancient civilization, using impeccable methods, and one concluded that it lasted 1,000 years while the other insisted it endured only 800. Both accounts can't be right, yet both are built on solid evidence. For cosmologists, that realization is both thrilling and terrifying. The two approaches probe different eras of cosmic history. The microwave background reflects conditions just after the Big Bang, while supernova observations capture the modern universe billions of years later. In principle, those two periods should be linked by the same physics, the same underlying equations. If they disagree, it means something changed in the middle, something our models failed to include. Perhaps the universe's expansion didn't proceed as smoothly as we thought. Maybe the ingredients of the cosmos' dark energy, dark matter, or the geometry of space itself evolved in ways that defy our assumptions. Or perhaps the discrepancy hints at a deeper flaw in the very laws we use to describe reality. These ideas might sound extreme, but they stem from desperation as much as curiosity. The methods themselves have been tested and cross-checked relentlessly. Astronomers have tried swapping the stars used as calibrators, adjusting for dust and recalibrating instruments aboard space telescopes like Hubble and Gaia. Each adjustment refines the precision but leaves the gap intact. Even when the brand new James Webb Space Telescope joined the effort, its sharper vision didn't reconcile the results. It confirmed the higher local rate of expansion. That left scientists staring at a paradox that grows sharper the more carefully it's examined. Some researchers have suggested that perhaps the local universe, the part we can observe in detail, just happens to sit in an unusual region, slightly emptier or denser than average, skewing our perception of cosmic motion. Others propose more exotic ideas, maybe dark energy, the mysterious force driving expansion, isn't constant after all but strengthens or weakens over time. Or perhaps there's an entirely new form of matter, or a modification to gravity itself altering the cosmic balance. Whatever the answer, the contradiction has forced physicists to confront the unsettling possibility that the elegant model, explaining nearly a century of observations, the so-called standard model of cosmology, might be incomplete. Every time astronomers measure the universe's expansion, they're not just mapping distances, they're testing the integrity of the laws that govern existence. And right now, those laws seem to be giving two contradictory answers. It's as though reality itself is whispering that our understanding, however sophisticated, is missing something profound. As the instruments of astronomy evolved, scientists expected the uncertainties to shrink and the numbers to finally converge. Better data, better telescopes, sharper measurements. Surely that would reveal which side of the expansion rate debate was correct. Instead, the opposite happened. Each new generation of technology made the discrepancy clearer, not smaller. The more precisely humanity looked at the universe, the more stubbornly it refused to fit the equations. When the James Webb Space Telescope began returning its first measurements, many believed the tension would finally dissolve. Webb's infrared sensitivity allowed it to see deeper into the cosmos than any telescope before it, tracing the flicker of ancient stars that even Hubble had missed. If any instrument could settle the matter, it was Webb. But instead of closing the gap, Webb confirmed it beyond doubt. Its readings of Cepheid variables, those pulsating stars that serve as cosmic rulers, matched the earlier higher expansion rate to an almost eerie degree. There was no error, no bias hiding in the data, no miscalibration to blame. The universe really was stretching faster than the Big Bang model predicted. What began as a technical disagreement had now hardened into a crisis of physics itself. Scientists started calling it the Hubble tension, a term that sounded polite enough at first but grew more ominous as the data poured in. When astronomers from independent teams reanalyzed Webb's results, using different techniques and statistical corrections, they reached the same conclusion again and again. The precision was so high that the chance of this discrepancy being random dropped to less than 1 in a million. This was no illusion. Something fundamental was missing from our understanding of how the cosmos works. To visualize the problem, imagine two clocks, each built with extraordinary craftsmanship, each synchronized with atomic accuracy. One clock measures time by looking at the faint echoes of the earliest universe, while the other measures the present moment using the motion of galaxies. Both are running flawlessly, yet one runs 6 minutes faster than the other, and no matter how often they are recalibrated, the difference persists. It's as though the universe itself is keeping two sets of time, two parallel truths that cannot both be real. That's the level of contradiction cosmologists face today. The James Webb Space Telescope, rather than being the great reconciler, became the messenger of bad news. Precision itself had become the enemy. Every decimal place added to the measurement made the problem more undeniable. For scientists who have built their careers on the elegance of mathematical consistency, this was deeply unsettling. In science, increased precision usually clarifies reality. Here, it made reality stranger. It was as if the universe, when examined under the sharpest lens ever built, had revealed a hidden fault line beneath the surface of our cosmic model. Theories that once seemed airtight now showed cracks. Some physicists began to wonder if the flaw lay not in the data, but in the foundation itself, in the assumptions passed down from Einstein's equations, the models that treat space as uniform and time as constant. If those principles begin to fail on the grandest scales, The consequences ripple through every corner of cosmology. The tension, as it deepened, became a philosophical crisis as well as a scientific one. What does it mean when two correct measurements contradict each other? What happens when our instruments agree, but our theories do not? These are the kinds of questions that challenge the very idea of scientific certainty. For decades, cosmology had been a success story of convergence, from the discovery of the cosmic microwave background to the measurement of dark energy. The pieces of the puzzle seemed to lock neatly together. Now, with Webb's unparalleled accuracy, that coherence was breaking down. The more clearly we could see, the less sense it made. Yet in the midst of the confusion, there was also a quiet thrill. Every time in history that precision has exposed contradiction, when Newton's gravity couldn't explain Mercury's orbit, or when black-body radiation defied classical physics, it has led to revolution. Maybe the Hubble tension was the cosmos's way of hinting that something even deeper waited to be discovered. Perhaps our universe was more dynamic, more intricate than any equation had captured. Still, the scientific community couldn't ignore the immediate implications. If the higher rate was real, then the universe might be younger than we thought, perhaps by hundreds of millions of years. If the lower rate was right, then something within the local universe was making nearby galaxies appear to move faster. Neither scenario was comforting. Each forced cosmologists to consider rewriting textbooks that had stood largely unchallenged for a century. The phrase, "faster than physics says it should," wasn't hyperbole. It was a literal description of the data. When the most advanced telescope ever built confirms that the cosmos itself is disobeying its own rules, the universe stops being a solved riddle and becomes a mystery again. And for scientists, that mystery, terrifying as it is also irresistible. Somewhere between 67 and 73 lies the truth, and finding it could mean unearthing a new law of nature or discovering that reality, in some deep and unfamiliar way, doesn't run on a single universal clock. The deeper the precision, the louder the question becomes. What is the universe trying to tell us? The more evidence poured in, the less the universe seemed willing to cooperate with our expectations. What began as a mild tension in the numbers soon turned into something much heavier, a word scientists rarely use lightly: a crisis. For years, cosmologists believed that given enough data, the disagreement between the two expansion rates would fade into statistical noise. Instead, the gap grew sharper, its boundaries more defined. Every time someone improved a telescope, refined a model, or recalibrated the math, the contradiction deepened, and the confidence in both sides grew stronger. By 2020, even the most cautious researchers were beginning to admit that this was no simple measurement error. In conference halls and published papers, phrases like "crisis in cosmology" started appearing. And when Dan Skolnick, one of the field's leading voices, publicly declared that the Hubble tension has become a crisis, it wasn't hyperbole. It was recognition that the foundation of modern cosmology might be incomplete. The irony was painful. Science had never been more precise, and yet its most fundamental question, how fast is the universe expanding, was more uncertain than ever. This wasn't supposed to happen. The standard model of cosmology, built on Einstein's general relativity and refined over nearly a century, was supposed to describe everything: how the universe was born, how it evolves, and how it will end. It had survived countless tests, from predicting gravitational waves to mapping the cosmic microwave background with astonishing precision. For a long time, cosmologists felt they were closing in on a near-complete understanding of the cosmos. But the Hubble crisis exposed a crack right through the middle of that understanding. The conflict was simple enough to state but profound in implication. If two independent and rigorous measurements of the universe's expansion disagree by a margin that cannot be explained by error, then one of two things must be true. Either something in the universe changed in a way we don't yet understand, or the laws we thought were universal are not quite what we believed. Neither option was comforting. At first, there was resistance. Many scientists urged patience, reminding colleagues that cosmic measurements had always contained uncertainties. They argued that the so-called crisis was more of an opportunity for refinement than a sign of failure. But as time passed, the numbers refused to bend. The cosmic microwave background continued to point to 67, while supernovae and Cepheids insisted on 73. The difference was too persistent, too consistent, and too large to dismiss. And so, the debate shifted from "is there an error?" to "what are we missing?" The deeper scientists dug, the stranger the possibilities became. Some proposed that dark energy, the mysterious force driving cosmic acceleration, might not be constant after all. Perhaps it changes over time, growing stronger or weaker depending on the universe's age. Others wondered if we might live in a cosmic bubble, a region of space slightly emptier than the average, giving us a distorted view of the expansion around us. There were even whispers of modifications to Einstein's equations, subtle adjustments that might explain why space seems to stretch faster on large scales than theory allows. Each hypothesis carried enormous consequences, not just for cosmology but for physics itself. If dark energy evolves, then our understanding of the universe's future changes completely. It might one day slow, stop, or even reverse its expansion. If we live in an atypical cosmic region, then our assumptions about what the universe looks like elsewhere could be wrong. And if Einstein's theory needs revising, then the very geometry of reality might operate differently than we've ever imagined. What truly elevated the situation from tension to crisis was the realization that both measurements were correct within their domains. The early universe calculation based on the cosmic microwave background was verified to extraordinary precision by missions like Planck, while the late universe measurement based on supernovae had been cross-checked with independent techniques like gravitational lensing and baryon acoustic oscillations. Neither side showed weakness. The universe appeared to be telling two different stories that were both true. In a sense, it was as if we were reading two chapters of the same cosmic book, written in different languages, describing the same event in incompatible ways. Translating between them became the greatest challenge in modern physics, and yet, amidst the frustration, there was a growing sense of excitement. Historically, every crisis in physics has been the birthplace of a breakthrough. The ultraviolet catastrophe led to quantum mechanics. The failure of Newtonian physics gave rise to relativity. Maybe this cosmic crisis was another turning point, a sign that something revolutionary was waiting beyond the horizon of current understanding. Scientists began to embrace the word crisis, not as a symbol of defeat but as a call to exploration. The universe had stopped behaving predictably, which meant there was something new to discover. Whether it was a new form of energy, a hidden property of gravity, or an unrecognized flaw in how we perceive time, the cosmos was demanding that humanity look deeper. The Hubble crisis was more than a scientific puzzle. It was a reminder that even in an age of precision and supercomputers, the universe remains mysterious, unpredictable, and alive with secrets yet untold. And for the first time in a century, cosmologists found themselves standing at the edge of the known, staring into the unknown, and realizing that the story of the universe might just be starting over again. At first glance, the argument over whether the universe is expanding at 67 or 73 kilometers per second per megaparsec might sound like a trivial numbers game. But this single value, the Hubble constant, isn't just another statistic. It's one of the most important quantities in all of science. It serves as a kind of cosmic ruler and clock at once, defining both the scale of space and the tempo of time itself. Every major cosmological model, every theory of how galaxies form, evolve, and eventually die, depends on this constant being correct. Change it, even slightly, and the entire history of the universe has to be rewritten from the ground up. The Hubble constant essentially tells us how quickly galaxies are receding from one another, which translates directly into the rate of expansion of space itself. If you know how fast the universe is expanding now, you can calculate how long it's been expanding its age and how large it has become. That means a higher value of the constant makes the universe younger and smaller, while a lower value makes it older and more stretched out. The difference between 67 and 73 doesn't just mean a few percent, it alters the estimated age of the cosmos by hundreds of millions of years. Imagine learning that Earth wasn't 4.5 billion years old, but 3.8 or 5.2 instead. The impact would ripple through every branch of geology, biology, and history. That's what cosmologists are facing. The Hubble constant is the foundation upon which cosmic history rests, and right now that foundation looks unstable. If the universe is expanding faster than expected, it might mean that some unseen force is adding extra energy to space. Or, conversely, if the slower rate is correct, maybe we've overestimated the power of whatever drives the expansion. Perhaps dark energy isn't behaving as we think, Either way, the implications touch everything from the nature of time to the fate of the universe itself. One reason this constant matters so much is that it links the smallest scales of reality, the quantum world, with the largest, the cosmic web of galaxies. It ties together measurements made by physicists studying subatomic particles with observations made by astronomers mapping the sky. In theory, the physics that governs atoms should also govern galaxies, because both exist in the same universe and obey the same laws. But if the Hubble constant refuses to line up, it suggests there's a missing connection between those realms, a gap in our understanding that stretches from the infinitesimal to the infinite. The stakes go beyond academic curiosity. A miscalculation of the Hubble constant could affect how we interpret gravitational waves, the bending of light by massive galaxies, and the way we estimate distances across the cosmos. Even our predictions for how stars form and die could change, since those depend on the density and age of the universe. In a way, this one number functions like the key in a piano. If it's even slightly off pitch, the entire symphony of the cosmos sounds wrong. Scientists rely on it to translate light into distance, distance into time, and time into meaning. Without it, the entire narrative of cosmic evolution becomes uncertain. Consider this. If the higher expansion rate is correct, then the universe is roughly 12.7 billion years old. If the lower rate holds true, it's closer to 13.8 billion. That's a difference of over 1 billion years. A staggering gap when you remember that the solar system itself is only about 4.5 billion years old. In that missing billion years could lie explanations for why galaxies formed when they did, why the cosmic web looks the way it does, and even why life had time to emerge at all. It's like discovering that the clock of existence might be ticking faster or slower than we thought, and we don't yet know which. The importance of the Hubble constant also extends into the future. The universe's expansion rate determines its ultimate fate, whether it will continue to accelerate forever, tearing galaxies apart until only lonely particles remain, or whether it might slow down, stop, and collapse in on itself in a final big crunch. A faster expansion rate implies a more energetic dark energy that could lead to a cold, empty end. A slower one suggests a gentler cosmic evolution that might one day reverse course. In other words, by measuring the Hubble constant, we're not just learning where the universe came from, we're glimpsing where it's going. This is why cosmologists are so obsessed with getting the number right. It's not pedantry, it's prophecy. It tells us whether the cosmos is infinite or finite, doomed or eternal. And that's why the current crisis feels so profound. A mismatch in the Hubble constant isn't merely a technical problem, it's an existential one. If our best measurements of the universe's expansion don't agree, then perhaps we've misunderstood something far more fundamental, the nature of reality itself. It's as if the universe is holding up a mirror, and in that reflection the neat picture humanity built for a century is starting to blur. To resolve that blur, scientists may need to rethink everything, from the forces shaping space-time to the mysterious energy accelerating it. Because in the end, that single number isn't just about speed. It's the heartbeat of the universe, and right now it's skipping a beat. Every new observation that should have brought clarity has instead deepened the mystery. Over the past few years, the most advanced surveys and telescopes have remeasured the Hubble constant with breathtaking precision, only to find that the universe's expansion appears to be even faster than before. One of the most striking results came from a study of the Coma cluster, a massive congregation of galaxies hundreds of millions of light-years away. By analysing the movement of these galaxies with refined data and upgraded instruments, scientists found an expansion rate of about 76.5 kilometers per second per megaparsec, an even greater value than the already controversial 73. This wasn't a fluke or a fringe result. It was another piece of solid, peer-reviewed evidence that something about the cosmos refuses to conform to expectations. With every decimal point of precision, the noose around conventional physics seems to tighten. What makes these new measurements so troubling is that they come from different methods, using different objects and instruments, yet they all converge on the same conclusion. The universe is expanding faster than our theoretical models predict. This is not a single telescope making a mistake. These are independent teams on separate continents, operating distinct observatories, all seeing the same phenomenon through different eyes. Astronomers have compared measurements using supernovae, Cepheid variables, gravitational lensing, and even quasars, those incredibly bright ancient beacons powered by supermassive black holes, and the story never changes. Every approach confirms the high value. At this point, the possibility of a systematic error is almost zero. The instruments are more accurate than ever, the calibrations more rigorous, the cross-checks more thorough. The tension isn't fading, it's solidifying into fact. And yet, the deeper the precision, the more absurd the implications become. If the universe is really expanding this quickly, then either some unknown force is pushing it harder than expected, or our fundamental picture of gravity is incomplete. For cosmologists, both explanations are monumental. The coma cluster result was especially provocative because it challenged one of the most deeply held assumptions in modern cosmology: that the laws of physics are the same everywhere. In theory, a galaxy cluster hundreds of millions of light-years away should behave according to the same rules as our local region of space. The speed of light, the pull of gravity, the effects of dark matter, all of it should be universal. Yet the data from the coma cluster hinted that either the expansion rate varies depending on where or when you measure it, or that some cosmic ingredient has been overlooked entirely. It's as if the universe itself is running multiple versions of the same operating system, each slightly out of sync with the others. In response, scientists have thrown every conceivable explanation at the problem. Could dark energy, the mysterious pressure that accelerates expansion, be growing stronger over time? Could dark matter interact with normal matter in ways we haven't detected, subtly altering how galaxies drift apart? Or maybe, as some have suggested, the very fabric of space-time is more complex than the smooth continuum Einstein described, a dynamic textured medium whose behavior shifts with cosmic scale. None of these answers are easy to test, but the data insists that something radical is happening. The irony is that this crisis stems from progress, not failure. A century ago, when Edwin Hubble first measured the expansion of the universe, his estimate was off by a factor of 10. The uncertainties were so vast that small discrepancies didn't matter. But as instruments improved, those uncertainties shrank, and what once looked like noise turned into a clear, measurable conflict. Today, telescopes can pinpoint the distance to a galaxy with an accuracy of less than 1%, and yet instead of unity, the result is division. We've reached the point where our precision has outpaced our understanding. The better we see, the less we comprehend. The tension has grown so famous that it now serves as a testing ground for new physics. Any theory that claims to describe the universe must now account for both expansion rates simultaneously. It's a tall order akin to reconciling two different realities into one coherent picture. Some theorists are even considering that the universe's early history might have included an episode of early dark energy, a brief burst of accelerated expansion that temporarily sped up the cosmos and left a lasting imprint on its current behavior. Others are exploring whether time itself flows differently in different regions of the universe, introducing a natural way to explain why expansion looks faster from our perspective. No idea is too strange at this point, because the traditional explanations have all failed. Every new dataset makes it clearer that something fundamental is missing. The numbers have become a riddle the universe refuses to solve for us. And so, the paradox tightens, like a cosmic knot that only becomes harder to untangle the more we pull at it. Each new observation is a reminder that precision, once a scientist's greatest ally, can also be a merciless judge. The coma cluster result didn't close the book on the mystery, it tore another page out and left the rest blank. For cosmology, it's both humiliating and exhilarating. The universe, it seems, still has surprises left, and it's daring us to figure them out. Somewhere within those expanding galaxies lies the truth, a truth that could rewrite physics, redefine time, and reshape our understanding of everything that exists. When the data began refusing to fit the established model, some scientists started to ask an unsettling question. What if the problem isn't with our measurements, but with the way we think about time and space themselves? Among those daring to look beyond conventional explanations is physicist David Wiltshire, whose radical proposal known as the timescape model challenges one of cosmology's deepest assumptions. In the standard picture of the universe, dark energy is the mysterious force driving the acceleration of cosmic expansion. It supposedly makes up about 70% of everything that exists, yet we've never detected it directly. It behaves like a kind of invisible pressure, pushing galaxies apart faster and faster as time passes. The discovery of this accelerating expansion in the late 1990s was so revolutionary that it earned its discoverers the Nobel Prize, cementing dark energy as a cornerstone of modern cosmology. But as the Hubble crisis worsened, Wiltshire and others began to suspect that dark energy might not exist at all, that what we interpret as acceleration could be nothing more than a misunderstanding of how time flows across the vast structures of the cosmos. The timescape model begins with a simple but profound observation. The universe isn't uniform. It's not a smooth soup of matter expanding evenly in every direction. It's a complex landscape of dense clusters, filaments, and immense voids regions where galaxies are few and far between. In these voids, gravity is weaker, and according to general relativity, that means time itself should flow slightly faster. Inside dense regions like galaxy clusters, gravity is stronger and time ticks more slowly. We already know this effect occurs on small scales, for instance. Clocks on satellites in orbit run slightly faster than clocks on Earth's surface, but Wiltshire argues that on cosmic scales, this difference in clock rates could become significant enough to mimic cosmic acceleration. Imagine the universe as a vast network of valleys and plateaus. Observers living in the dense valleys of galaxy clusters experience slower time, while the emptier plateaus of cosmic voids experience faster time. When astronomers in one of those valleys, such as our Milky Way, look out across the expanding universe, they're effectively comparing their slower local clock with the faster clocks of distant regions. To them, it appears as though those regions are speeding away at an increasing rate. But the acceleration might be an illusion, a trick of perspective caused by the uneven flow of time itself. If this interpretation is correct, then there's no need for a mysterious repulsive energy permeating space. The apparent acceleration could emerge naturally from general relativity once we take into account that time doesn't pass uniformly everywhere. In other words, the universe might not be accelerating at all. We just experience time differently depending on where we are. Wiltshire's model is bold because it questions the very concept of cosmic time, a single universal clock that ticks identically throughout the cosmos. In most equations, physicists assume that such a clock exists. It's what allows us to speak of the universe having a single age, like 13.8 billion years. But the timescape idea suggests that this assumption is too simplistic. There might not be one cosmic time, but a patchwork of local times, each shaped by its surrounding gravitational environment. When averaged together, these differences could produce the illusion that the universe as a whole is accelerating. This theory doesn't just offer a way to explain the Hubble tension, it reimagines the entire framework of cosmology. If correct, it means the concept of dark energy is unnecessary. The cosmic expansion behaves differently across scales, and the age of the universe might vary depending on where you measure it. Some regions could be billions of years older or younger in their own frame of reference. Critics argue that the timescape model, while elegant, is difficult to test directly. Measuring time flow differences across billions of light years is an enormous challenge. Still, upcoming missions like the European Space Agency's Euclid Telescope and NASA's Nancy Grace Roman Space Telescope are expected to gather data precise enough to either support or rule out Wiltshire's predictions. If his theory is confirmed, it would rank among the most profound discoveries in the history of science, rivaling even Einstein's relativity and its implications. It would mean that the cosmos isn't governed by a single ticking rhythm, but by a symphony of clocks, each marking the passage of time in its own unique way. For now, the idea remains controversial, but it has gained attention precisely because it offers a way to reconcile the universe's conflicting expansion rates without inventing new physics. In a sense, Wiltshire's hypothesis reminds us that the greatest mysteries sometimes emerge not from what we can't see, but from how we see it. Maybe the universe isn't accelerating because of an invisible force. Maybe it's our perception of time itself that's warped by the vast, uneven structure of reality. In that view, the Hubble crisis isn't a cosmic malfunction. It's a clue, pointing toward a deeper truth about the nature of time and the limits of human understanding. For most of the 20th century, cosmology relied on a simplifying assumption that on the larger scales, the universe is smooth, uniform, and the same in every direction. This principle, known as the cosmological principle, made the math of Einstein's general relativity manageable and elegant. By averaging out all the galaxies, clusters, and voids into a uniform cosmic fluid, scientists could describe the behavior of spacetime with relatively simple equations. Those equations, called the Friedmann-Lemaitre-Robertson-Walker models, became the backbone of modern cosmology. They told us how the universe expands, how it cools, and how it evolves. But as technology improved and telescopes mapped more of the cosmos in detail, it became clear that the universe is anything but smooth. What we once thought of as a simple, even distribution of matter, turned out to be a breathtakingly intricate web, a structure so vast and complex that it defies easy simplification. Galaxies don't float evenly through space. They cling to immense filaments of dark matter and gas, threading together into clusters and superclusters, with enormous voids spanning hundreds of millions of light-years between them. This cosmic web is one of the grandest structures in nature, and its discovery forced physicists to confront a difficult truth. The equations that describe a smooth universe might not capture the messy reality of the one we live in. The smoother the assumptions, the more convenient the math, but also, perhaps, the less accurate the conclusions. When Einstein and Friedmann first applied relativity to the universe, they did so at a time when the large-scale structure was unknown. To them, treating the cosmos as homogeneous was a reasonable approximation. But in reality, the gravitational fields around galaxies and voids bend time and space differently. The dense regions where galaxies form experience stronger curvature, slowing the passage of time, while the vast empty voids where little matter exists allow time to flow more freely. When we pretend the universe is smooth, we erase those differences, averaging away the very features that might hold the key to understanding cosmic expansion. The timescape model, and others like it, emerge from this realization. They argue that the unevenness of the universe, the clumping of matter and the emptiness between, must be built into our understanding of cosmology from the start. Ignoring it might lead us to false conclusions, such as the belief that an unknown dark energy is driving acceleration. In this view, the apparent speeding up of expansion could simply be a side effect of living in a lumpy, uneven universe where time and gravity play tricks on our measurements. The concept isn't just philosophical, it's deeply mathematical. When physicists average out the density and curvature of space to create a smooth universe, they also average out the distortions caused by gravity. But general relativity doesn't behave linearly. You can't just blend all the local variations together and expect the result to reflect reality. The sum of curved spaces isn't equal to a single smooth curvature. This means that the real universe, with all its lumps and voids, might expand differently than the simplified models predict. If that's true, then our current cosmological equations could be subtly but significantly wrong. Evidence supporting this idea comes from high-resolution surveys like the Sloan Digital Sky Survey and the Dark Energy Survey, which reveal just how extreme the variations in density and structure can be. The cosmic web's voids, which make up most of the universe's volume, aren't just empty. They might play an active role in shaping cosmic evolution. In these regions where gravity is weak, expansion can proceed faster, while in denser areas it slows down. The result is a patchwork cosmos, where different parts of space stretch at slightly different rates. To observers like us situated inside a relatively dense region, that differential could appear as an overall acceleration of expansion. This interpretation doesn't eliminate the mystery entirely, but it shifts the problem from exotic new physics to the subtleties of Einstein's existing framework. Perhaps the universe doesn't need invisible energy to explain its behavior. Perhaps it only needs a more careful accounting of how gravity, space, and time interact across its uneven landscape. The notion of a non-smooth universe also raises profound philosophical questions. If every region of space experiences time differently, can we truly speak of a single cosmic now? When we say the universe is 13.8 billion years old, whose clock are we using? Ours, anchored in a galaxy bound by gravity, or one ticking freely in the emptiness of a cosmic void? The deeper scientists probe these questions, the clearer it becomes that the simple, elegant cosmological principle may have been a useful fiction, an approximation that has finally reached its limit. The universe, it turns out, is messy. It's asymmetrical, dynamic, and full of local quirks. And in that messiness may lie the solution to the most perplexing riddle in physics. The cosmos isn't a smooth ocean of expanding space. It's a stormy sea, with waves, troughs, and whirlpools that bend both space and time. The challenge now is to build a theory vast enough to contain that complexity, one that sees the universe not as a perfect equation, but as a living, evolving structure, a universe that may be expanding unevenly, because it was never uniform to begin with. To understand how gravity might create the illusion of an accelerating universe, we need to revisit one of Einstein's most extraordinary insights, that gravity is not a force pulling objects together in the traditional sense, but a distortion in the fabric of space and time. Massive objects like stars, planets, and galaxies bend this fabric, and the greater the mass, the deeper the curvature. This warping affects not only the motion of objects, but also the flow of time itself. The stronger the gravity, the slower time runs. This phenomenon, known as gravitational time dilation, has been proven repeatedly. Atomic clocks flown on satellites or planes tick faster than identical clocks on Earth's surface. Even a difference of a few thousand meters in altitude can produce a measurable shift in time's passage. While such variations are tiny on human scales, over cosmic distances they can accumulate to produce astonishing effects. Imagine a clock placed in the heart of a galaxy cluster, surrounded by trillions of stars whose combined gravity drags on space-time like an anchor. Now imagine another clock floating in the near emptiness of a cosmic void, where gravity's grip is faint. The clock in the void will run slightly faster than the one in the cluster. Over billions of years, those differences compound until the two clocks disagree by huge amounts, possibly by hundreds of millions of years. Wiltshire's timescape model takes this idea and extends it to the entire universe. From our vantage point inside a relatively dense region, the Milky Way, within a filament of the cosmic web, our local experience of time may be slower than in the vast low-density voids that dominate the cosmos. When we look outward and observe distant galaxies receding, we're effectively comparing our slower clock to their faster ones. The result is an illusion. Those galaxies seem to be accelerating away from us, not because space itself is expanding faster, but because their clocks are ticking differently from ours. In this framework, cosmic acceleration becomes not a property of space, but a byproduct of perspective. It's the same effect that makes GPS satellites require time corrections to function properly. From their point of view, Earth's clocks are running slow due to the planet's gravity. To us, their clocks seem to run fast. Neither is wrong. Both perspectives are valid within their own frames of reference. The difference lies in the curvature of space-time between them. On Earth, the correction amounts to nanoseconds. Across the universe, the discrepancy could amount to eons. To visualize this, think of two runners moving along different sections of a racetrack, one on flat ground, the other on a steep slope. To an observer unaware of the slope, the runner on the incline appears to be accelerating relative to the one on the flat ground. But in reality, both are running steadily. It's the terrain itself that changes. In cosmological terms, that terrain is space-time, and its varying curvature creates the illusion of acceleration. Gravity doesn't just distort the paths of objects, it distorts our perception of time, and with it, our interpretation of motion. In a perfectly smooth universe, where matter is evenly distributed, these effects would cancel out. But in our real, uneven cosmos, filled with clumps and voids, the distortions accumulate asymmetrically. Light from distant galaxies travels through both dense and empty regions, being stretched and delayed along the way. When we observe that light, we interpret its stretching as evidence of an accelerating expansion. But what if the light's journey simply crossed zones where time itself flowed at different speeds? The result would look identical, even though the underlying physics would be radically different. If this interpretation is correct, it could mean that the universe isn't being pushed apart by some mysterious dark energy. It's simply that our cosmic clocks aren't synchronized. The acceleration would be a mirage, born from our position within a gravitationally slower region. In that sense, the universe may be far less mysterious than we think, but also far more intricate. Our measurements might be distorted not by faulty instruments, but by the very structure of space-time itself. This realization blurs the boundary between observation and perspective. When cosmologists measure the Hubble constant, they're not just taking snapshots of distant galaxies, they're peering across billions of years of unevenly flowing time. The light we see carries not just information about where those galaxies are, but about how fast their time was ticking when the light left them. If time itself varies from one region to another, then comparing those regions directly could be like comparing seconds to minutes without realizing the units have changed. The implications of this are staggering. It means that our current models of cosmic history might be missing a crucial dimension, the dynamic rhythm of time itself, stretched and compressed by gravity's invisible hand. In that sense, the apparent tearing of space could be a reflection of time's uneven heartbeat. The cosmos might not be expanding faster than physics allows. It might simply be reminding us that physics itself is inseparable from the clocks by which we measure it. As revolutionary as the timescape hypothesis sounds, a theory remains only speculation until it can be tested. That's the challenge facing modern cosmology: how to prove or disprove whether time itself truly flows differently across the vast, uneven structure of the universe. For the first time in history, humanity has the instruments capable of making that determination. The coming years will see an unprecedented wave of space missions designed to map the cosmos in exquisite detail, and their data could finally reveal whether the apparent acceleration of the universe is a mirage born of time dilation or genuine evidence of dark energy. At the forefront of this effort is the European Space Agency's Euclid telescope, launched with the goal of creating a three-dimensional map of billions of galaxies across more than a third of the observable universe. Euclid isn't just photographing galaxies, it's measuring their shapes, distances, and the subtle distortions in their light caused by gravity, what scientists call weak gravitational lensing. By analysing how light bends as it travels through cosmic structures, Euclid can infer the distribution of both visible and invisible matter, revealing the geometry of the universe with incredible precision. This map of cosmic curvature is crucial because it allows cosmologists to test whether the expansion rate is truly uniform or varies depending on where and when it's measured. If Wiltshire's timescape model is correct, Euclid should detect tiny but systematic differences between regions dominated by voids and those rich in galaxy clusters, differences that would indicate time doesn't flow evenly everywhere. Complementing Euclid will be NASA's Nancy Grace Roman Space Telescope, scheduled to survey the skies with a field of view 100 times larger than Hubble's. Roman will specialize in measuring cosmic acceleration through several independent techniques, by observing Type Ia supernovae, tracking baryon acoustic oscillations, the ancient ripples left from the early universe, and mapping dark matter through precise gravitational lensing data. Its instruments will capture light from galaxies so distant that it has travelled for over 10 billion years, offering a continuous record of how cosmic expansion has changed over time. Together, Euclid and Roman form a kind of cosmic interrogation team, designed to ask the universe two key questions. Is the acceleration of expansion constant across all directions, and does it behave as the standard model predicts? If the answer is yes, dark energy remains the dominant explanation. If not, if time appears to vary with environment, it would provide the first observational support for the timescape hypothesis. Such a result would overturn the need for dark energy entirely, and replace one of the biggest mysteries in physics with a new understanding of relativity on cosmic scales. The beauty of this test is that it's empirical. It doesn't rely on philosophical arguments or theoretical speculation, but on measurable phenomena: light, gravity, and geometry. The timescape model predicts distinct patterns that can, in principle, be observed. For example, if clocks in cosmic voids run faster, galaxies within those regions should appear slightly older and redshifted differently than galaxies of similar distance in denser environments. That pattern, if found, would be impossible to explain with dark energy alone. On the other hand, if Euclid and Roman find no such discrepancies, it would deal a serious blow to Wiltshire's idea and reinforce the view that something like dark energy really does exist. Either outcome would be transformative. A confirmation would mean rethinking the very nature of cosmic time and rewriting decades of textbooks. A refutation would strengthen confidence in the standard model and push researchers to refine their understanding of dark energy's properties. For cosmologists, both results are equally thrilling because each leads to deeper truth. Testing the timescape hypothesis also matters because it embodies the essence of science itself, a willingness to question even the most sacred assumptions when confronted with conflicting evidence. For a century, physicists have treated time as uniform on cosmic scales, a single clock governing all of reality. But nature may not be so tidy. Perhaps time is as local as gravity, shaped by the matter around it. If that's the case, then measuring it demands instruments capable of seeing not just across distance, but across difference. The Euclid mission has already begun sending back its first maps, revealing astonishing detail in the distribution of galaxies. Early glimpses suggest an even richer structure than scientists anticipated, a tapestry of filaments and voids that could hold clues to the cosmic flow of time. Meanwhile, the Roman telescope, set to launch soon, promises to extend that reach and tie those observations together into a coherent narrative. In the next decade, cosmology will either confirm that space is truly tearing itself apart, or that we've been fooled by our own perspective. The outcome could redefine our understanding of everything from gravity to destiny itself. For now, scientists wait, sifting through streams of data, searching for the faint fingerprints of time's uneven rhythm across the universe. Whether the result vindicates the timescape model or buries it, one thing is certain. The act of testing it marks a turning point. Humanity is no longer satisfied with staring into the heavens for beauty or wonder alone. We're listening for the ticking of the universe's clocks, trying to hear whether they all keep the same time. Even as missions like Euclid and Roman prepare to test whether time itself flows unevenly across the cosmos, another set of observations is quietly hinting at something just as radical, that dark energy. The mysterious pressure believed to be driving cosmic acceleration might not be constant at all. For decades, cosmologists have treated dark energy as a simple, unchanging property of space, an invisible force uniformly filling the universe. It was assumed to be the same everywhere and everywhen, described by a fixed number in Einstein's equations called the cosmological constant. But recent findings from a vast project known as the Dark Energy Spectroscopic Instrument, or DESI, are starting to challenge that view. DESI's mission is as ambitious as it sounds. Mounted on a telescope in Arizona, it uses 5,000 robotic fiber optic sensors to collect light from millions of galaxies and quasars, measuring their precise redshifts, the stretching of their light due to cosmic expansion. By mapping these redshifts across billions of years of cosmic history, DESI can reconstruct how fast the universe was expanding at different epochs. The first major results from this survey surprised even its creators. The data hinted that the strength of dark energy might have changed over time. In the early universe, billions of years ago, the rate of expansion seemed slower than what a constant dark energy model would predict. But later, it began to speed up more dramatically. In other words, dark energy may not be a fixed feature of reality, it may evolve. If that's true, it means we're living in a dynamic universe, where the very rules that govern its expansion are shifting with time. The implications of such a discovery are enormous. If dark energy grows stronger, the universe will continue accelerating, stretching galaxies ever farther apart until they vanish beyond one another's reach. But if it weakens, the expansion could slow down or even reverse, leading to an entirely different cosmic destiny. Either way, the idea that dark energy changes introduces a new variable into the equations that define the cosmos. It's as if the universe has moods, expanding with different intensities depending on its age. This evolving dark energy model could also help explain the Hubble tension. If the energy driving expansion wasn't constant but slightly stronger in the present era than in the past, it could reconcile why local measurements show a higher rate of expansion than those derived from ancient light. That would mean both camps are right. The early universe did expand more slowly, consistent with 67, while the modern universe really is expanding faster, around 73, because dark energy's influence has grown over time. Instead of contradiction, the discrepancy becomes evolution. Cosmologists call this idea dynamic dark energy, or quintessence. Unlike the cosmological constant, which remains the same forever, quintessence imagines dark energy as a field, some as yet undiscovered form of energy that can change its strength and behavior. It might ebb and flow, decay, or even oscillate. In this view, space isn't a passive stage where events unfold, it's an active participant, capable of changing its own properties over time. The DESI data isn't yet definitive, but it's compelling enough that many physicists are beginning to take this idea seriously. It opens a new path through the maze of contradictions that have haunted cosmology for years. Instead of rewriting gravity or inventing new kinds of matter, perhaps we only need to accept that dark energy itself has a history. The concept of a changing dark energy also connects with earlier cosmic mysteries. In the universe's infancy, just moments after the Big Bang, there was another burst of acceleration known as inflation, a rapid expansion that shaped everything we see today. If inflation was driven by a temporary field of energy, perhaps dark energy is a similar phenomenon operating on a slower, gentler scale. Maybe the universe has experienced multiple phases of accelerated expansion, each driven by a shifting energy field woven into the fabric of space. If that's true, it could mean that dark energy and inflation are two faces of the same underlying principle, a cosmic cycle of expansion that waxes and wanes like tides. Some researchers have even proposed that this energy might one day reverse itself, causing the universe to stop expanding and begin contracting again. That possibility may sound catastrophic, but to many cosmologists it's a natural expression of the universe's rhythm. Expansion followed by rest, growth followed by renewal. For now, the evidence is tantalizing but incomplete. DESI's first results have opened the door, but it will take years of data and analysis to determine whether dark energy truly evolves. Upcoming surveys from Euclid and Roman will help confirm or refute the pattern. If they agree, it would mean that the universe's most dominant force is not eternal and unchanging, but a live and evolving entity with its own cosmic timeline. It would transform our understanding of space, energy, and fate. The idea that dark energy has a pulse turns the cosmos from a static clockwork into a living, breathing system. It implies that the future of the universe is not predetermined, but unfolding in ways we're only beginning to glimpse. What seemed like a cold, mathematical void may instead be a dynamic ocean, shifting and surging as it expands into eternity, or perhaps one day begins to draw back in. For more than 2 decades, the dominant narrative in cosmology has been that the universe is expanding at an ever-increasing rate, driven by a mysterious dark energy that seems to defy gravity itself. But what if that story is beginning to change? What if the cosmic acceleration, far from continuing indefinitely, has already started to slow down? This provocative idea has gained traction through the work of Youngwook Lee and his colleagues, who analysed a vast collection of astronomical data and noticed patterns that challenge the prevailing picture. Their results suggest that the universe may have entered a new phase 1 where expansion is no longer speeding up, but gradually losing momentum. It's a hypothesis that, if proven true, would rewrite our expectations for the future of everything. Lee's team began with a simple question. What do the most distant supernovae really tell us about cosmic acceleration? For years, Type Ia supernovae, the brilliant explosions of dying stars, have served as the primary evidence for the discovery of dark energy. Their consistent brightness allows astronomers to use them as standard candles, measuring how fast galaxies are receding. The dimmer the supernova appears, the farther away it is, and from that relationship the rate of expansion can be inferred. When this method was first applied in the late 1990s, it revealed that the universe was expanding faster than expected, a discovery that transformed cosmology. But Lee's reanalysis found something curious. When he extended the data to include both very distant and relatively nearby supernovae, the pattern wasn't perfectly smooth. Instead, it hinted at a subtle shift in behaviour. At earlier times, expansion did seem to accelerate, but in more recent epochs, the rate appeared to level off slightly, as if the cosmic push of dark energy were beginning to weaken. That small deviation might seem insignificant, but across billions of years it could mean that the universe has already passed its peak expansion rate. If so, we may be living in a transitional era, the point where the outward rush of space begins to ease, and gravity starts to reassert its influence. The consequences of that shift are profound. A slowing expansion would imply that dark energy is not constant, echoing the hints found by the DESI survey. Instead of a steady, unchanging force, it might behave more like a spring that has been stretched too far and is now starting to relax. That would mean the universe's expansion is not an unstoppable acceleration toward isolation and emptiness, but part of a larger cycle of rise and fall. In this picture, the cosmos could one day halt its outward motion and gradually begin to contract, setting the stage for a distant Big Crunch, a mirror image of the Big Bang. Lee's research doesn't claim that a collapse is imminent, only that the signs of deceleration may already be visible in the data. If correct, it would mean that the universe has reached a kind of cosmic turning point, a midpoint between endless expansion an eventual contraction. The notion is both unsettling and strangely poetic. It paints the universe not as a runaway phenomenon racing toward oblivion, but as a self-balancing system governed by deeper rhythms. Critics caution that the apparent slowdown might be an artifact of measurement uncertainties or biases in the supernova data. Observing objects billions of light-years away is an inherently difficult task, and even small errors can accumulate into misleading trends. Yet as more observations pile up from supernovae, galaxy surveys, and cosmic microwave background studies, the possibility of changing acceleration becomes harder to dismiss. Some cosmologists suggest that the shift could be linked to interactions between dark energy and dark matter, two invisible components that together make up nearly all of the universe. If dark energy draws energy from dark matter, it might lose strength over time, allowing gravity to slow the expansion. Others propose that we're simply misinterpreting the geometry of the cosmos, that the observed deceleration is a natural outcome of living in a region where local structures distort our perception of cosmic motion. Whatever the explanation, the idea of a slowing expansion has reawakened an ancient question. Is the universe eternal, or does it have a natural life cycle? For centuries, philosophers and scientists have imagined cosmic histories that repeat in endless loops of creation and destruction. Now, with modern data hinting at a possible slowdown, that ancient vision is taking on new scientific form. If the current acceleration is temporary, then the universe we know is part of a larger story, a breathing cosmos that expands and contracts across eons, endlessly reinventing itself. For now, the evidence remains inconclusive. The data is subtle and the models are complex, but the very fact that scientists are asking these questions shows how far the field has evolved. Just a few years ago, the idea of deceleration would have been dismissed outright. Today, it's being taken seriously, tested with the best instruments humanity has ever built. Whether or not the slowdown proves real, it reminds us that even the grandest cosmic truths can change. The universe is not static. It evolves, surprises, and sometimes contradicts our deepest assumptions. Maybe the acceleration was never permanent. Maybe it was just another chapter in an ever-shifting cosmic rhythm that may one day lead back to the beginning. If the universe truly is slowing down, if the acceleration that once pushed galaxies apart is fading, then the next question is unavoidable. What happens if expansion eventually stops altogether? The answer is both fascinating and terrifying. In this possible future, the universe reverses its direction, not immediately, not within any human lifetime, but across billions of years, and begins to fall back inward. This idea, known as the Big Crunch, is the mirror image of the Big Bang, a cosmic rewind in which everything that has ever existed is drawn back together under the inexorable pull of gravity. For most of the 20th century, the Big Crunch was considered a real possibility. Before dark energy was discovered, cosmologists debated whether gravity would eventually overcome the momentum of expansion. If there were enough matter in the universe, enough mass packed into galaxies, stars, and invisible dark matter, then gravity could slow expansion to a halt and pull everything back in. For decades, that question boiled down to one number: the density of the universe. If it was above a critical threshold, the cosmos would end in fire. If it was below, it would expand forever. When the discovery of cosmic acceleration came in the late 1990s, the Big Crunch seemed to be ruled out. Dark energy's repulsive effect appeared to guarantee an eternal expansion. But if dark energy can change, weaken, or even vanish, as recent evidence might suggest, then the universe could one day find itself without that outward pressure. Gravity, patient and relentless, would then begin to dominate again. Over unimaginable spans of time, the expansion would slow further until galaxies stopped drifting apart. At first, the change would be subtle. Distant galaxies that once redshifted away would appear to hover, their retreat stalling as the fabric of space stopped stretching. Then, ever so slowly, they would begin to move closer. The light from the most distant stars would blue shift, growing brighter and hotter as space compressed. Clusters of galaxies would start to merge, and the cosmic web that now stretches across billions of light years would begin to contract like a tightening net. Over hundreds of billions of years, the sky would grow crowded again. Galaxies that are now too far away to ever see would reappear, moving toward one another as the universe shrank. Eventually collisions would become inevitable. Stars would crash together, forming enormous supermassive black holes. The vast emptiness between galaxies would disappear, replaced by a dense, chaotic maelstrom of energy. As the contraction continued, the temperature of the universe would rise. The cosmic microwave background, the faint afterglow of the Big Bang that now whispers across space, would brighten and shift into visible light, then into blinding radiation. What we now call the cold, dark cosmos would once again blaze. Time itself might begin to behave differently. Just as expansion stretches the intervals between events, contraction would compress them. From a human perspective, cosmic history would seem to speed up, with galaxies colliding and stars igniting in rapid succession. Near the end, as matter became densely packed, space-time would grow increasingly unstable. The gravitational pull of the collapsing universe would distort everything, bending light and time until the distinction between past and future blurred. In the final moments, all matter, radiation, and even black holes would merge into a single, infinitely dense pointer singularity, resembling the one that marked the universe's birth. That moment, the Big Crunch, would be the end of everything, and, perhaps, the beginning of something new. Some theories suggest that such a collapse could trigger a new Big Bang, a cosmic bounce that starts the cycle anew. In that vision, the universe doesn't die but transforms, oscillating endlessly between expansion and contraction, creation and destruction. Each cycle might produce slightly different conditions, different laws, even different forms of matter and life. It's a vision that combines physics with poetry, the cosmos as a breathing entity, inhaling and exhaling across eternity. Of course, no one knows if the Big Crunch will truly happen. The evidence for a slowing expansion is tentative, and dark energy's true nature remains a mystery. It could weaken and reverse, or it could intensify, tearing space apart in a big rip instead. But the mere possibility of a collapse is enough to remind us that cosmic permanence is an illusion. The universe is not a frozen system. It's a dynamic, evolving reality governed by balance. The same gravity that once drew matter together to form stars and galaxies could one day reclaim it all. From our perspective, these are almost unimaginable timescales, hundreds of billions or trillions of years into the future, but the physics is simple. What expands can also contract. The Big Crunch remains one of the most haunting possibilities in cosmology. It represents both an end and a renewal, destruction and creation, in the same breath. Whether the universe will fade into cold emptiness or collapse into fire is unknown, but either path carries a strange beauty. In both, the cosmos completes its story, reminding us that even the largest structures in existence are not beyond the reach of time. The stars, the galaxies, even space itself, all are temporary patterns in an ever-changing universe, and if the Big Crunch awaits, it will not be a failure of physics but the final act of its greatest masterpiece. As astronomers struggled to reconcile the conflicting expansion rates of the universe, one of the most intriguing possibilities to emerge was that dark energy might not be a single, timeless force at all. Instead, it could be something that flickers in and out of existence, an actor that takes the stage only at certain moments in cosmic history. This idea, known as early dark energy, was proposed by physicists at institutions like MIT and Princeton as a way to explain two of the biggest puzzles in modern cosmology, the Hubble tension and the strange abundance of bright, massive galaxies revealed by the James Webb Space Telescope. According to this hypothesis, dark energy didn't first appear several billion years after the Big Bang, as traditionally assumed. Rather, it showed up much earlier, perhaps when the universe was only a few 100,000 years old, and briefly altered the rate of expansion before fading again. That early burst of repulsive energy would have pushed the universe to expand slightly faster during its youth, changing how matter clumped together and leaving subtle imprints in the cosmic microwave background. Then, after lying dormant for billions of years, dark energy would have reawakened in the more recent past, causing the current era of acceleration we observe today. This two-stage history, an early flash and a late resurgence, could elegantly explain why the universe appears to be expanding faster now than models based solely on the Big Bang predict. It bridges the gap between the lower expansion rate inferred from ancient light and the higher rate measured in the local universe. Both results could be right, they're just capturing the cosmos at different chapters of its story. The early dark energy model also offers a potential solution to a second mystery: why Webb is observing galaxies that are far too bright and massive to fit the standard timeline. When the telescope first looked deep into space, it saw galaxies that had formed astonishingly soon, after the Big Bang, some appearing just a few 100 million years old but already containing billions of stars. According to conventional theory, there shouldn't have been enough time for such structures to form. Early dark energy could change that. By briefly speeding up the expansion at a critical moment, it would have allowed matter to cool and collapse into galaxies sooner, giving the universe a head start on building complexity. In this view, the early cosmos wasn't a slow simmer but a flash of intense activity, a kind of cosmic adolescence that set the stage for everything to come. The concept of early dark energy draws inspiration from the physics of inflation, that mysterious event at the universe's birth when space expanded exponentially in a fraction of a second. Inflation ended long before stars existed, but if similar energy fields can reappear under the right conditions, it's conceivable that smaller, milder bursts of expansion could occur later. The idea is that space itself might contain latent fields that occasionally activate and then fade, like embers reigniting in a dying fire. Each activation changes the expansion rate and reshapes the universe's structure. Testing such a theory is difficult but not impossible. The fingerprints of early dark energy would show up in several observable ways: tiny shifts in the cosmic microwave background, changes in the pattern of large-scale galaxy clustering, and differences in how ancient hydrogen gas absorbs light. Cosmologists are now combing through data from Planck, DESI, and soon Euclid to search for those subtle signals. If the pattern matches, it would confirm that the universe experienced at least two phases of accelerated expansion, one in its infancy and another in its middle age. That would be a profound discovery, linking the beginning of time to the present in a single unified picture. However, not everyone is convinced. Critics warn that introducing early dark energy risks complicating an already intricate model without sufficient proof. Adding extra phases of acceleration might solve one problem only to create others, such as inconsistencies with nucleosynthesis, the process that forged the first elements, or with the formation of the cosmic web. Yet even skeptics admit the idea is worth pursuing because it represents a middle ground between radical alternatives like modified gravity and the increasingly unstable cosmological constant. It doesn't rewrite the laws of physics, it merely adds a new layer to them. The beauty of the early dark energy hypothesis is that it makes sense of both the past and the present. It explains why the early universe looks older than it should, and why today's expansion rate appears too high. It offers a bridge between two eras of cosmic mystery, turning the apparent contradictions in the data into a coherent narrative. Whether it proves correct or not, it captures a growing realization among physicists. The universe may be far more dynamic than once believed, not governed by a single unchanging energy, but by a sequence of evolving stages. Perhaps the cosmos has always been this way, pulsing, cycling, and reinventing itself across the ages. In that light, early dark energy isn't just a theory about expansion. It's a reminder that the universe itself is a living process, full of echoes, recurrences, and surprises waiting to be uncovered. To grasp why ideas like early dark energy and inflation exist at all, we have to revisit the riddles that first forced scientists to rethink the early universe: the horizon problem and the flatness problem. These two puzzles sit at the foundation of cosmology, and solving them was what originally gave rise to the theory of cosmic inflation, a breathtaking concept that changed our entire view of how the universe began. The horizon problem starts with a simple observation. When we look at the cosmic microwave background, the faint afterglow left over from the Big Bang, we see light that has travelled across the universe for nearly 14 billion years. That ancient radiation is astonishingly uniform. No matter where we point our instruments, the temperature is almost exactly the same, varying by less than 1 part in 100,000. At first glance, this might seem unremarkable, but it's actually one of the greatest mysteries in science. Regions of the sky that are now separated by tens of billions of light years appear to have exactly the same temperature, even though they should never have been in contact. According to the standard Big Bang model, the universe expanded too quickly for light or heat to travel between such distant regions. There simply hasn't been enough time for them to exchange information or energy, and yet, somehow, the cosmos looks perfectly balanced, as though every part of it agreed on a single temperature before being torn apart. How could distant regions that were never connected end up so similar? That's the horizon problem, the mystery of cosmic coordination across impossible distances. The second riddle, the flatness problem, is just as strange. When cosmologists study the geometry of the universe, they find that space is extraordinarily flat, meaning that, on the larger scales, parallel lines stay parallel, and the angles of a cosmic triangle add up to 180 degrees. In Einstein's theory, the curvature of space depends on the total energy density of the universe. If there's too much matter, gravity curves space inward like a sphere. If there's too little, it curves outward like a saddle. But the current balance is so precise that the total density must have been tuned to within 1 part in 100 trillion at the time of the Big Bang. If it had been even slightly different, the universe would have either collapsed long ago or expanded too fast for galaxies to form. That kind of precision seems absurdly unlikely. Why should the cosmos start off so perfectly calibrated? In the late 1970s, physicist Alan Guth proposed a radical solution to both problems at once: inflation. He suggested that, in the first tiny fraction of a second after the Big Bang, the universe underwent a brief but stupendous burst of exponential expansion, growing from subatomic size to cosmic scale almost instantly. During that brief era lasting perhaps 10 to 32 seconds, space itself stretched by a factor of at least 10 to 26. This violent expansion would have had several miraculous consequences. First, it would solve the horizon problem by allowing all regions of the universe to have once been close enough to exchange heat and energy before being blown apart. The uniformity we see in the cosmic microwave background would then make sense. Everything was once in contact before inflation separated it. Second, inflation would explain the universe's near-perfect flatness. As space expanded faster than light, any initial curvature would have been stretched so thin that, from our perspective, it would appear completely flat, just as the curved surface of the Earth looks flat to someone standing on it. Inflation was an elegant fix, and for decades it stood as the leading explanation for the universe's remarkable uniformity and geometry. Yet even as it solved 2 major puzzles, it opened a Pandora's box of new questions. What caused inflation? What stopped it? And could it happen again? Modern cosmologists now suspect that inflation wasn't a one-time event, but part of a deeper pattern, perhaps linked to early dark energy, or even to a self-renewing process where new universes constantly bubble into existence within a larger cosmic multiverse. The seeds of all structure galaxies, stars and planets were planted by tiny quantum fluctuations during inflation. Those minute ripples in density stretched across the universe became the scaffolding of everything we see today. The cosmic web itself, with its filaments and voids, is the frozen fingerprint of that ancient event. The remarkable consistency between inflation's predictions and the cosmic microwave background's patterns is what gives scientists confidence that something like it really happened. Still, the mechanism behind it remains mysterious. The field that drove inflation, called the inflaton, has never been observed, and its nature is unknown. Some models imagine it as a quantum field embedded in space. Others treat it as an emergent property of higher dimensions, or as a precursor to dark energy. Whatever it was, it changed everything. In less than a heartbeat, it transformed the universe from a chaotic quantum foam into a smooth, structured cosmos. That transformation solved the horizon and flatness problems and provided the foundation for modern cosmology, but it also hinted at a profound truth, that the universe's apparent order may have been born from an instant of unimaginable chaos. And just as that chaos gave rise to everything we know, it may yet hold the key to understanding why the universe continues to evolve in such mysterious and beautiful ways. If inflation was the spark that set the universe expanding, then quantum mechanics was the brush that painted its intricate structure. One of the most remarkable ideas in modern physics is that every galaxy, every star, and every atom in your body can trace its origin back to microscopic fluctuations in energy that occurred during the universe's first heartbeat. Inflation didn't just stretch space, it magnified the smallest quantum tremors into vast ripples that became the scaffolding of everything we see today. To understand this, imagine the early universe as a boiling sea of energy. At that unimaginably small scale, the laws of physics are governed not by certainty but by probability. Quantum fields fluctuate constantly, their energy densities rising and falling in random bursts. Most of these fluctuations cancel out almost instantly, but during inflation, something extraordinary happened. Space itself expanded so rapidly that these tiny blips were frozen in place, their random wiggles stretched across cosmic distances. What was once a subatomic irregularity became a structure spanning light years. Over billions of years, gravity would amplify those faint differences in density, pulling matter towards slightly denser regions. Those regions became the first stars and galaxies. In a very real sense, the entire cosmic web was written into existence by the random noise of quantum mechanics. When we look at the large-scale structure of the universe, the vast filaments of galaxies connected across billions of light-years, we're seeing a fossilized record of those primordial fluctuations. The cosmic microwave background too carries their signature. Its faint temperature variations, mapped in exquisite detail by satellites like COBE, GMAP and Planck, are the direct descendants of quantum ripples from the first instant of creation. The data shows a pattern of slightly warmer and cooler spots, revealing where matter was just a little more or less dense. Those minute imbalances, no larger than 1 part in 100,000, were enough to tip the cosmic scales. Without them, the universe would have remained perfectly smooth, and no galaxies, stars, or life would ever have formed. The fact that quantum randomness seeded the structure of the cosmos is one of the most profound insights in all of science. It connects the smallest possible scale, the quantum realm, with the largest, the structure of the universe. This link between the microscopic and the cosmic suggests a unity in nature that goes far beyond what early scientists could have imagined. Inflation was the bridge that made this connection possible. It acted like an amplifier, taking the tiniest vibrations of the quantum vacuum and turning them into the blueprint for galaxies. The process is a perfect marriage of Einstein's general relativity and quantum mechanics, two theories that usually exist in tension. Here, they work together beautifully. Relativity describes the stretching of space, while quantum mechanics provides the initial irregularities that get stretched. The harmony between these two pillars of physics is striking, yet incomplete, because we still don't know exactly how they merge. The early universe remains the ultimate testing ground for that unification. In a sense, the universe itself was a quantum experiment, a spontaneous fluctuation that went unimaginably right. Over time, those ancient ripples grew into the filaments and voids we now observe with telescopes like Euclid and the Dark Energy Survey. The filaments mark regions where matter pooled. The voids show where it was sparse. Together they form a cosmic web so vast that it resembles the neural network of a brain. This resemblance isn't just poetic. Both systems organize complexity from simple rules. In the brain, electrical impulses between neurons form thoughts. In the universe, gravity acting on density fluctuations creates galaxies. The underlying principal order emerging from chaos is the same. What began as random noise has evolved into breathtaking structure. Even the distribution of galaxies follows patterns predicted by the mathematics of quantum fluctuations. That means we can, in principle, trace the lineage of every cluster, every star, and every planet back to a jitter in the quantum vacuum 13.8 billion years ago. This idea that the entire cosmos arose from microscopic uncertainty redefines what we mean by creation. It suggests that randomness and order are not opposites but partners in the unfolding of reality. The smallest possible disturbances can shape the grandest possible structures, given enough time and space. Quantum mechanics gave the universe its texture, inflation gave it its scale, gravity gave it its form. The interplay of these three forces produced the vast web of galaxies stretching across the night sky. And perhaps the most astonishing part of all is that this entire chain of events was inevitable once the first spark of inflation began. Every fluctuation, every filament, every galaxy was encoded in those quantum seeds, waiting to unfold. When we gaze into the darkness between the stars, we're not just looking at distant light, we're witnessing the frozen echo of quantum vibrations that once danced in the smallest corners of existence. The cosmic web is, in essence, the universe's memory of its own birth, written not in words or symbols, but in the geometry of space itself. Once the quantum seeds from inflation had been sown, the next great sculptor of the cosmos took over: gravity. From that moment on, the universe became a grand construction project, driven by the invisible pull of matter and the silent guidance of dark matter, the unseen framework that gives the cosmos its shape. Over billions of years, gravity turned those faint density ripples in the early universe into the magnificent structure we now call the cosmic web, a vast network of filaments, clusters, and voids stretching across the observable cosmos. The story begins roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. Until that moment, it had been an opaque plasma, where photons scattered endlessly off free electrons. Once the temperature dropped sufficiently, light could finally travel freely, creating the cosmic microwave background, the first light we can see today. But the moment transparency arrived, gravity began its slow, relentless work. Slightly denser regions, marked by the faint temperature variations left by quantum fluctuations, began to attract more matter. Over millions of years, those regions grew denser, pulling in hydrogen, helium, and dark matter. The process was self-reinforcing. The more mass a region contained, the stronger its gravitational pull became, drawing in even more material. This is the essence of cosmic structure formation, tiny imperfections expanding into grand architecture. Yet dark matter was the true engineer of this design. Although we cannot see it, we know it makes up about 85% of all matter in the universe. It does not emit or absorb light, but its gravity influences everything that does. Without it, the universe's visible matter would never have coalesced into galaxies. The expansion of space would have scattered everything too quickly. Dark matter acted like an invisible scaffold, forming enormous filaments that extended across space. Regular matter gas, dust, and eventually stars simply followed the contours of that unseen structure. Over time, these filaments interconnected into vast networks, with dense knots forming at their intersections. Those knots became galaxy clusters, the largest gravitationally bound systems in the universe. Within these clusters, smaller filaments and halos gave rise to individual galaxies, each containing hundreds of billions of stars. The cosmic web, mapped by modern telescopes and simulations, resembles a three-dimensional spider's web made of light. The filaments stretch for hundreds of millions of light years, and the voids between them are immense expanses almost entirely empty of matter. This pattern is not random. It's the natural outcome of gravity acting on the quantum blueprints of the early universe. Supercomputer simulations like the Millennium Run and illustrious TNG have recreated this process in astonishing detail. Starting with the initial conditions from the cosmic microwave background, these digital universes evolve under the known laws of physics, and the resulting structures look nearly identical to what we observe in reality. The resemblance is so precise that scientists can now zoom in on simulated galaxies and predict how their shapes, spins, and star populations develop over billions of years. Through these simulations, we've learned that the cosmic web isn't static, it's dynamic and alive. Filaments funnel gas and dark matter into galaxies, feeding star formation. Voids expand, pushing clusters farther apart. Galaxies merge, collide, and ignite bursts of starbirth before settling into new shapes. The universe's structure is constantly evolving, an endless dance between attraction and expansion. And yet, through all this complexity, a striking harmony persists. Whether on the scale of a single galaxy or the entire observable universe, the same patterns repeat: networks, nodes, filaments, and flows. It's a kind of cosmic fractal, a self-similar geometry that spans from the microscopic ripples of the quantum field to the colossal arcs of galaxy clusters. Even our own Milky Way sits inside one of these filaments, bound to its neighbours in the Virgo supercluster, a region so vast it would take tens of millions of years for light to cross. Beyond that lies the Laniakea supercluster, a continent of galaxies stretching 500 million light-years across, all connected by invisible threads of dark matter. Every point in the sky, every twinkle of starlight, belongs to this immense architecture. Gravity designed it, dark matter built it, and time refined it. The cosmic web isn't just the universe's structure, it's its memory. It preserves the imprint of the initial fluctuations from inflation and records the slow, methodical hand of gravity sculpting chaos into order. And as we map it with increasing precision through surveys like Euclid, DESI, and the Vera Rubin Observatory, we're not just charting space, we're uncovering the universe's biography, layer by layer. In every filament and void lies a record of cosmic evolution, a story billions of years in the making. The architecture of the universe is both colossal and delicate, a masterpiece of physics woven from randomness and gravity. It reminds us that even the grandest structures can arise from the smallest imperfections, and that within the quiet pull of gravity lies the blueprint for everything we are. Inside the vast latticework of the cosmic web, galaxies were born like sparks in a cosmic forge. Each one began as a ripple in the early density field, a slightly denser pocket of matter surrounded by a halo of dark matter. Over hundreds of millions of years, gravity drew gas into these invisible halos, compressing and heating it until the first stars ignited. Those ancient stars, blazing into existence when the universe was less than 1 billion years old, transformed darkness into light. They mark the beginning of structure, chemistry, and complexity. But the formation of galaxies was anything but peaceful. It was a violent and chaotic process, driven by the constant tug-of-war between gravity, radiation, and motion. In the early epochs, small dark matter halos merged together, forming larger and larger systems. These collisions were frequent and catastrophic. Each merger released enormous amounts of energy, compressing gas into starburst regions and igniting the birth of countless new suns. Over time, this hierarchical merging built the grand galaxies we see today. The process was guided entirely by dark matter's invisible hand. Every galaxy sits inside a dark matter halo, a spherical envelope of unseen mass that extends far beyond the visible stars. These halos act as gravitational anchors, holding galaxies together and governing how they spin. Without them, the outer stars in spiral galaxies would fly off into space, unable to stay bound by visible matter alone. This realization came in the 20th century when astronomers like Vera Rubin studied the rotation curves of galaxies and found something strange. Stars far from the galactic center weren't slowing down as expected. They were moving just as fast as those closer in. The only explanation was that an enormous amount of invisible mass surrounded each galaxy. Dark matter, though unseen, defines the very architecture of galactic life. Within these halos, ordinary matter gas and dust cools, condenses and forms rotating disks. Gravity pulls the gas inward while angular momentum keeps it spinning, flattening it into the elegant spirals we recognize in galaxies like the Milky Way or Andromeda. In some cases, gas collapses more violently, creating elliptical galaxies, vast spheroids of old stars left behind by ancient collisions. Others remain irregular, chaotic systems shaped by turbulence and time. In the early universe, galaxies were smaller, denser, and more active. The first generations of stars were massive and short-lived, burning through their fuel in just a few million years. When they exploded as supernovae, they scattered heavy elements, carbon, oxygen, iron into surrounding space, enriching the gas from which later stars would form. That enrichment was crucial, setting the stage for planets, life, and everything familiar. Every atom in our bodies was forged in the hearts of those early stars, then dispersed through the cosmos by their deaths. Galaxies, in that sense, are engines of creation. They recycle matter endlessly, turning gas into stars and stars back into gas. Over billions of years, they evolve through a delicate balance of inflow and feedback. Gas flows in from the cosmic web, stars form and die, and their explosions heat and drive the remaining gas outward. This feedback regulates growth, preventing galaxies from forming all their stars at once. It's a self-sustaining ecosystem that keeps galaxies alive. The Milky Way itself grew through countless mergers, swallowing smaller companions and absorbing their stars. Even now it continues to consume dwarf galaxies at its edges, pulling them in with tidal streams that stretch across the sky. One day, it will collide with its nearest large neighbour, the Andromeda Galaxy. Simulations suggest that in about 4 billion years, the two will merge, their stars swirling into a single giant elliptical galaxy, an act of cosmic renewal rather than destruction. Such mergers are common, shaping the destiny of every galaxy. The traces of these events can still be seen in the ripples and warps of galactic disks, in the faint halos of scattered stars that surround them. Each galaxy is a history book written in starlight, preserving the memory of every collision and transformation. But despite their differences in shape and size, all galaxies share the same basic anatomy: a dark matter halo that provides mass and stability, a luminous core of stars, and a network of gas inflows and outflows that sustain star formation. This universal structure is no coincidence. It's the outcome of the same laws of physics applied across all of space and time. Galaxies are the universe's way of organizing matter into meaning, turning chaos into order, and raw hydrogen into complexity. As we peer deeper into the cosmos with instruments like the James Webb Space Telescope, we're seeing galaxies in their infancy, small, irregular, and brimming with energy. They are snapshots of our own Milky Way's distant past, showing how the universe matured from simplicity to grandeur. Every glimmer of starlight we capture is a message from an age when the first structures were taking shape, when gravity and dark matter were still weaving the cosmic tapestry. The story of galaxy formation is, ultimately, the story of how the universe learned to build. From randomness came architecture, from chaos came light. And within that light the seeds of everything we know began to bloom. At the heart of nearly every large galaxy lies a paradox, a region of absolute emptiness that governs everything around it. Supermassive black holes, with masses millions or even billions of times greater than the Sun, sit at galactic centers like cosmic engines. Though they are objects of pure gravity from which not even light can escape, their influence extends far beyond their event horizons. These titans of space not only consume matter, but also regulate the growth and fate of entire galaxies. Their presence ensures that galaxies, despite their vastness, remain balanced and self-regulating rather than collapsing into chaos. The connection between galaxies and their central black holes was not always obvious. For decades, astronomers viewed black holes as exotic oddities, interesting but largely irrelevant to the universe's overall story. That changed in the 1990s when researchers discovered a striking correlation. The mass of a galaxy's central black hole is directly linked to the mass of its bulge, the dense central region of stars. The bigger the black hole, the bigger the galaxy. This relationship, known as the M-sigma relation, revealed a profound truth. Galaxies and their black holes evolve together, locked in an intricate feedback loop. When matter falls toward a supermassive black hole, it doesn't always vanish immediately. Instead, much of it forms a swirling accretion disk, a ring of superheated gas and dust orbiting at incredible speeds. Friction and magnetic forces within the disk cause it to blaze with energy, sometimes outshining the entire galaxy. These brilliant outbursts are called quasars, or active galactic nuclei, and they can release more energy than all the stars in their host galaxies combined. For a brief time, the black hole becomes a beacon visible across billions of light years. But this outpouring of energy is not merely spectacular, it's transformative. The radiation and powerful winds from quasars can blow away vast quantities of gas, halting star formation in their host galaxies. In doing so, the black hole effectively throttles its own growth as the same gas that fuels it is expelled. This process, known as feedback, acts as a cosmic thermostat. Too much gas leads to rampant star formation and rapid black hole feeding. Too much feedback clears the galaxy of its fuel. The result is equilibrium. The galaxy and its central black hole evolve in harmony, each regulating the other's behavior through cycles of outburst and calm. Without this delicate feedback, galaxies would likely look very different. They might grow endlessly, forming far more stars than observed, or collapse under their own weight. Instead, we see a balance spirals, ellipticals, and irregulars all maintaining a consistent ratio of stars to total mass. The hidden hand of the black hole keeps them from tipping too far in either direction. In our own Milky Way, the central black hole, Sagittarius A, has a mass of about 4 million suns. For most of its existence, it has been relatively quiet, occasionally flaring but mostly dormant. Yet even this calm giant shapes the life of the galaxy. Its gravitational influence affects the orbits of nearby stars, and its past outbursts have left faint traces, vast bubbles of hot gas rising above and below the galactic plane, evidence of ancient eruptions millions of years ago. Those Fermi bubbles, as they're known, stretch tens of thousands of light-years into space, reminders that even a sleeping black hole can have a long reach. Across the universe, similar interactions unfold on grander scales. When galaxies merge, their central black holes spiral toward one another, eventually coalescing in a titanic event that releases gravitational waves ripples in space-time itself. These mergers help seed new activity, triggering bursts of star formation and reshaping galactic structure. In that sense, black holes are both destroyers and creators. Their violent energy births new generations of stars while also keeping galaxies from becoming overgrown. Quasar feedback, stellar winds, and supernova explosions all work together in a self-organizing process that keeps the cosmic ecosystem stable. The physics behind this balance is astonishingly complex, but the outcome is simple: harmony. Galaxies are not chaotic accidents. They are regulated systems sustained by feedback loops that echo life itself, cycles of growth, regulation, and renewal. Without black holes, the universe might be unrecognizably different. There would be no graceful spirals, no well-ordered clusters, perhaps no habitable worlds at all. The same gravity that consumes also gives shape, maintaining a delicate equilibrium on which all structure depends. Every time we look into the bright heart of a distant galaxy and see the flicker of a quasar, we're witnessing that balance in action, a cosmic heartbeat, pulsing across billions of light years. These black holes, silent yet powerful, remind us that even the darkest places in the universe can be engines of light, structure, and order. They are the regulators of creation, ensuring that the universe does not simply burn out or collapse, but endures structured, balanced, and astonishingly alive. From the first flickers of quantum fluctuations to the birth of stars, galaxies, and black holes, the universe has been a story of transformation, a grand evolution from simplicity to complexity, from chaos to structure, from darkness to light. But every story eventually faces its end, and cosmologists have long pondered how this one will close. Will the cosmos continue expanding forever, growing colder and more isolated with each passing eon? Will it slow, collapse, and be reborn in a fiery big crunch? Or will it tear itself apart in a final unimaginable act known as the Big Rip? The ultimate fate of the universe depends on a single question: what happens to dark energy? If it remains constant, as Einstein's cosmological constant suggests, then the expansion will go on forever. Galaxies will drift beyond one another's reach, and the night sky will slowly empty. Stars will exhaust their fuel, planets will grow dark, and even black holes will evaporate through Hawking radiation, leaving only a thin mist of photons. This heat-death scenario describes a future in which the universe doesn't end in fire but in silence. A cold, motionless sea where entropy reaches its maximum and nothing more can happen. It's not an explosion but an eternal fading, a cosmic whisper stretching into infinity. Yet if dark energy changes over time, as new evidence increasingly implies, then other endings become possible. If its strength diminishes, gravity might eventually regain control, halting the expansion and pulling everything back together. The universe would begin to contract, galaxies merging and collapsing into a dense inferno. Time itself could speed up as space shrinks until everything matter, light, even the laws of physics implodes into a singular point. That would be the Big Crunch, the mirror image of the Big Bang, and in some speculative theories, such a collapse might not be the end at all but a transition, a cosmic rebirth, a bounce that ignites a new universe from the ashes of the old. The cosmos could be cyclical, breathing in and out over unimaginable epochs. In that vision, every beginning is an echo of an earlier ending, and our universe is just one heartbeat in an infinite pulse of creation and destruction. Then there is the most terrifying possibility of all, the Big Rip. If dark energy grows stronger over time instead of fading, it could eventually overwhelm every force in existence. First, it would pull galaxies apart. Then it would rip stars from their orbits, planets from their suns, and molecules from one another. In the final moments, even atoms would be torn asunder as the fabric of space-time itself shreds. Time would cease to have meaning. The cosmos wouldn't end in silence or collapse, it would dissolve. Whether our universe dies in heat, collapse, or rupture, each scenario speaks to a profound truth. Nothing lasts forever. The universe, like everything within it, evolves and transforms. But that impermanence isn't tragic. It's what makes existence possible. Every atom in your body was born in the furnace of a dying star. Every breath you take carries the history of ancient galaxies. Even the most fleeting moments of consciousness are built from matter forged in cosmic violence. To exist at all is to be part of the universe's grand cycle of creation and decay. In that sense, our fate is inseparable from the fate of the cosmos itself. We are not observers standing apart from it, we are its latest expression, temporary and miraculous. For all our technological advances, for all the telescopes and equations that let us peer into the depths of space, the greatest revelation of cosmology may be its most humbling, that the universe is both infinitely vast and intimately connected to us. The same laws that shaped the first atoms govern our thoughts, our stories, our sense of wonder. Whether the cosmos ends in cold emptiness or bursts anew in light, our existence proves that the universe is capable of awareness, however fleeting. When we study the stars, the universe is in a sense studying itself. Every discovery from dark energy to cosmic inflation brings us closer to understanding not just where we came from, but what it means to be. Perhaps that's the true purpose of cosmology, not to predict the end, but to appreciate the fragile beauty of the present, to realize that amid all the uncertainty, the equations, and the distant galaxies, there is meaning in simply being here, alive in a moment when the universe can look back upon itself and wonder. No one knows how this story will conclude. The universe may fade, collapse, or renew, but as long as there are minds to question and eyes to see, its story continues. We are the universe's way of understanding its own impermanence, of giving voice to the silence between the stars, and that, perhaps, is its most extraordinary creation of all.